Novel Java Coding Chronicle. My name's Andrew Twigg and I'm the Sales Director. As you've logged in today, I'm sure most of you know who Chronicle are and who Peter is, so I'll keep the introduction brief. Peter Lorre is CEO of Chronicle Software. He founded Chronicle in 2013, and over the past 7 years, the company has grown significantly, both in open source downloads and enterprise customers. Currently, our open source software is downloaded over 17 million times per year, and the enterprise side of the business is due to hit $3 million in revenue, growing by over 30% this year alone. Peter's a Java champion, and he's one of the global leading experts in Java development with the most answers on Stack Overflow. He's also driven the use of Java in low latency, opening up the skills and capabilities required to build the most demanding app, and he continues to research and develop innovative ways to utilize Java within the low latency microservices architecture. The format today is that Peter's going to run through his presentation, which includes many coding examples, and after which he'll answer questions. If you have any questions during the presentation, please submit them via the chat function in Zoom, and I'll present them to Peter at the end. So over to you, Peter.
Right, so what we're going to be talking about today are some of the sections of code within Chronicle. In particular, most of it's in Chronicle core library that are quite novel in the sense that if you looked at the code, you might wonder, why on earth did they do that? Or I didn't even know that that was something you might want to do. So I thought that might be interesting to people, and for people using Chronicle, it might be useful to know what it is that what we're doing and why. So the first thing I came to that's inspired this talk was the class we have called StackTrace. Now we use that for both tracking and logging stack traces. Now the thing that's interesting about that is that it's a throwable which does not extend either error or exception. If you have a look in Java, and I think in most libraries, if there are any throwables, they're either extending exception or error. But this one doesn't extend either, and the logic behind that is that it's not actually intended to be really thrown. It is not actually an error. It's a stack trace to determine, to record where this stack trace was taken. And an interesting method that comes with this class is the for-thread method. What it does is it creates a stack trace to record the thread's name, and then gets the current stack trace off the thread itself and then populates it, so that if you were to log this stack trace, you could easily say, print out not only that a thread is alive, for example, but also a stack trace of what that thread is doing. We use this in a number of places where we expect a thread to shut down, for example, but it doesn't. We can log programmatically, well, what is it doing? You know, why isn't it? Give you some idea as to why it hasn't shut down. When an object is created, record where it was created, but also log it. So in the code below, this is a sort of method that's called, maybe in a finalized block, to complain if the object was discarded without being closed. As you can see, it's very easy to put the created here stack trace in as the throwable associated with the illegal state exception message. But at the same time, if tracing is not turned on, that would just add a null, and therefore you still get the exception, but you just don't see the cause or something to trace it. So this is useful because it allows us to, so if an object is discarded, we can go back to, well, where was it created? And then work out, well, if it was created here, where should it have been closed? In many cases, if you get a discarded object, it can be a struggle to figure out, well, where in the code was it created in the first place? And this enables it, makes it very easy to track down. Also tracing if it's been closed. So say you try and use a resource after it was closed. It can be very useful to know, well, I'm trying to use it. I expected this not to be closed. So why was it closed? Well, we can trace the location of where it was closed. And then when we trigger an error, we can say, well, hey, it's closed, and it's because you closed it here. Right, this is where you closed it. Now, notice the stack trace also includes the thread. So along with the closed here message, you'll see the named thread. So in particular, this is useful if one thread is closing a resource while another thread it ends up using it or trying to use it, then you can see that in this error message. We use an integer here to reduce the overhead of, say, using an atomic boolean, or the somewhat vagaries of just using volatile, because you can't do a get and set with a volatile. So here's a more complex example where we go through and track down all of the threads that are still running after a test, and then we can report them as a single exception. Right down the bottom, you can see that AE in this case is an assertion error. And what we do is we create a stack trace for all of the threads that are still running. Not only can you see the name of the thread, but you can also see a stack trace of that thread. We've trimmed it down slightly. We trim it down slightly so that it's not quite so verbose, the entire stack trace. So you don't see the whole stack trace, but you see all the relevant information. And then that's added to as a pressed stack trace. And so you get a single exception, but it has multiple layers. You can see all of the threads that are running, what they're doing, and that will give you hopefully give you an idea as to why they are still running. That makes managing stack traces, monitoring threads, a lot easier to have this tool. So in short, this is why we have a stack trace that extends throwable, but not error or exception. So as you saw, we take stack traces async in other threads as they happen. This has the downside that it has the weakness that a thread has to reach a save point. And the save points the JVM will try and remove the save points for efficiency purposes. You don't always get a good picture of precisely where the time was being spent or where the thread was locked up. So it can be useful to deliberately add in save points where you believe that this is causing a problem, or it is obscuring where the true source of the delay was. So we've got a special method called SavePoint, which will not be optimized away in either Java 8 or Java 9. We've got different implementations because neither of them work across both of them. So we have to use a different implementation in each case.
Is it safe to use unsafe, since Oracle tries to make that modular?
It's definitely not safe to use unsafe. It requires significantly more testing if you do use it. I would say, as an estimate, you want to spend between 10 and 20 times as much testing and checking if you've used unsafe. We've also developed some methodologies around checking it for validity, ensuring it doesn't kill the JVM if you use it incorrectly. And a lot of this goes into Bytes, which is a library built on top of core. It is definitely to be used with caution. However, we still believe the performance benefits you get from using it outweigh its disadvantages. And in fact, there are some things you can do with unsafe that you just simply cannot do via other existing APIs. So in particular, one of the things we do in Chronicle Map is that we can map in a 64-bit region of memory. In reality, it's never more than about 40 bits, but in any case, it's more than 32 bits. And we do thread-safe operations on it. As yet, neither byte buffer nor even the replacements are designed for 64-bit regions of memory. They're all still sitting at 32-bit to my knowledge. Byte buffer doesn't support any thread-safe operations, though I believe the newer APIs do. The newer operations are safer, but they don't provide the same functionality, unfortunately. Another way to achieve the same functionality would be to not use unsafe, but rather use JNI. The problem with using JNI is that that can introduce an overhead, which can largely defeat the benefits of using unsafe as an intrinsic. Do need to support Java 8 still, and we will for some time. And none of the newer APIs, to my knowledge, have been backported to Java 8 or will ever be. Until we no longer need to support Java 8, we can't really move off unsafe, no matter how good the replacements are. So here's an example of what we do we add hints to spinning loops as well to reduce the burden on very tight loops. With Java 9, they added a method which is a spin weight hint. In Java 8, we just revert back to a regular save point. Another useful class we have, this is based on a class that's been around since Java 7 called class value. We have another implementation called class local, and it essentially supports taking a lambda for creating the instance instead of having to subclass class value. What does this do and why is it useful? Well, it allows us to cache decisions made about classes. So in this case, it caches the read resolve method for a class. And it only has to look it up once, right, ever for a particular class. And it's also retains a weak reference to the class. So if the class ever gets unloaded, this all gets cleared out correctly, which is quite nice. So in this case, it saves having to look up whether the read resolve method exists. And if it does exist, having to create a new one each time or throw an exception, both of which are expensive. So it just allows us to cache many of the decisions we make about in reflection to do with classes. And this saves, so there's a bit of overhead the very first time all these things happen, but once you repeatedly access the metadata to do with the class, it's all cached from then on. Another thing we make use of is Vocation Cast. And vocacious means to do without care or consideration. And what it allows us to do is to rethrow throwables without having to worry about whether they're checked or not. I have an example here where we have a class called throwing consumer instead of consumer. A throwing consumer can throw a checked exception and it will be handled appropriately. Got a whole bunch of throwing whatevers. However, if you need to adapt it and pretend that it's actually a normal consumer that doesn't throw a checked exception, we can wrap it, as you can see here, and we just pretend that it's going to be thrown, but in reality, it gets rethrown, as it were, without consideration of the fact that it's checked. So what happens is that the checked exception can still be caught encapsulating code as the original exception. It's not being wrapped at all. Can be slightly confusing. So it's important to decide whether this really helps and makes the code clearer, or it just makes things more obtuse, because it is turning off a feature that some people find frustrating, which is the checked exceptions. So some people might find that confusing. In general, when we've done this, we use it within our own code base. That is, where it's thrown and where it's caught is also in our code base. So you don't actually see that this is what's happening. But the benefit is that we can pass around the true checked exception and catch that checked exception without having to wrap it through code that itself wasn't written to handle checked exceptions. So this is the slide that got the most interest on Twitter when I was trying to promote this, and that was about using rounding for doubles rather than, say, using big decimals. So I was trying to come up with something that would justify why it is that we still encourage use of doubles in terms of benchmark. But part of the reason is not purely about speed, it's just about development. One of the problems that Java has, say, compared to C#, is it has no native language support for a decimal type. C# does. And that means that the code for big decimal is much more verbose and cumbersome and is not as easy to read. And as a result, it can be, in my opinion, error-prone compared to the readability of something that has natural language support. So that's my primary objection against big decimal, is actually just the readability of the code, being able to figure out what all these brackets are doing and all the different types. However, it also has a performance disadvantage. And in some cases, but not in all cases, but in some cases, that performance difference really matters. So I did a benchmark of multiplying. So this is a realistic use case. One of our applications actually does this in its own demos, which is to multiply a covariance matrix against a vector of positions. And that is basically 32 by 32 multiplication against a vector of 32 by 1. I ran this against 3 different versions of Java, comparing doing the same operation with the same values using big decimal versus double. And in every case, not only is double faster, But interestingly enough, Java 11, which uses a different GC by default, a different garbage collector by default, does a better job of reducing the peaks jitter associated with allocating double arrays. Now, in our use case, we don't actually create the double arrays, we recycle them. But the library I used here, which is Commons Math, does create new objects. So it does show up a bit of a spike, even for double on the 4 nines. But in a more realistic use case, even that wouldn't appear. And you would get a result closer to what you do with Java 11 or Java 14. As you can see that the margin, this is a logarithmic scale. So the difference is a factor of about 3 or 4 times, which I'll admit doesn't always matter. But if you include the overhead of readability for big decimal, then I would still favor using double. Another thing which doesn't get talked about enough, I think, is that when double is wrong, there's a rounding error or a representation error. It's clearly wrong. And you can usually infer what the value should have been. Like there'll be usually something like 99999 or 0000001, right? So you can work out, well, they shouldn't be there. It should have been rounded, right? If you forget to round it. The problem with big decimal is it'll always produce a number that looks appropriate, whether it's right or not. So if you say, for example, do a division by 7 and then multiply by 7, unless you do the rounding properly, you won't end up with the number you started with, but you will end up with a number that looks like it could be right. It doesn't stand out that this is a number that's wrong. So doubles, you're more likely to get errors, but you're more likely to be able to fix them and say, oh, this is obviously an error. Big decimal, you're less likely to get some sort of rounding or representation error, but if you do get one, it will be more of a surprise and not as obvious from just looking at the values. Another thing we've introduced recently in an attempt to ensure that resources are always cleaned up is have a thread we use in thread pools that when the thread has finished, will attempt to go through and clean themselves up. So in particular, this comes around thread locals. If you have a thread local and that contains a resource that needs to be closed, there is no trigger to ensure that that actually gets closed in Java built in. You either have to have a queue of weak resources and a background thread that goes through and cleans them up. This only happens after a GC, so it's not deterministic. It's not at the time the thread actually dies. It's a resource that could accumulate. Whereas using this approach, what happens is that using reflection, we go into the table when the thread actually dies, its own thread local table, and just find out if there's anything that needs cleaning up. And if it has, then it calls the cleanup method on each of those values. The nice feature there is that if you've got a thread local closable resource, it will be closed off deterministically as soon as that thread has finished for whatever reason. Another thing we use in our applications is we tend to use microsecond timestamps for recognizing and tracing messages passing through the system. This has 2 benefits. One is that you can see the time, more or less, but you can also, in using this kind of mechanism, ensure that it's unique within the code as well, within that system. What that does is it uses a piece of shared memory for it to store a long, and it ensures that timestamp hasn't been provided to any other process also using that shared memory. So that way, the microsecond timestamps are also unique across the entire machine, or for that user anyway, because at the moment, it doesn't share timestamps with different users. So for a particular application, all running as the same user, all of the timestamps will be unique that are generated by this application. And then that assists in tracing going through the system as well. So we have an interesting class, which its job is to essentially intern or object pool strings or data that can be turned into strings as it comes into the system when it's deserialized in particular. What's interesting about it is not that the thread pool that this object pool exists, but the fact that the object pool itself doesn't need any explicit thread safety constraints to operate correctly on a thread-safe environment. So string itself has some thread safety guarantees. All of the fields that are final will be visible between threads, and there's nothing that is additional required. There's no access to a volatile or any kind of locking. That string will still be correctly visible across all threads if it can be seen at all. The array here, so we've got an array, which is basically like a hash array, contains references to strings. Now, it is possible that different threads will have different strings in them, but for the purpose of what this collection does, that doesn't actually matter. All that we need is access to a string in a hash. If that string matches, then we return it. If the string doesn't match, then we try a second slot, and if the second slot doesn't work, then we create a new one, we overwrite it. There may actually be some inherent advantage for two threads if they're working on different data sets to actually have different views of what are actually in this array. But if a third thread comes along and tries to use this, it doesn't really matter which of the two it ends up in. I think this one's interesting because it's a collection that's safe to use between threads without any explicit thread safety guarantees. I've not come across any other that works like this in our code base or anywhere else, but so I thought that's why it might be interesting. So one of the nice things you get with checked exceptions is you can ensure your documentation is correct. You can ensure that your APIs actually say what exceptions you expect to be thrown. What if you're trying to avoid clients having to track all of these exceptions that might be very rare, but you still want to document it, right? So you want to use unchecked exceptions, but you still want to make sure your documentation's right. The trick I use is I temporarily add a class that's a checked exception that's in the same package as the unchecked one. And then what the compiler does is it goes through and complains that, oh, you're not throwing this checked exception, or you're not handling it, or you're not documenting it. In most cases, then the IDE has auto fixes for it. So it's not as tedious as it sounds to go through and correct it all. So you just go through, accept all the auto fixes. Eventually, your code will actually show where this unchecked exception really is being called. First time I did this, I actually came across lots of examples where the code thought this unchecked exception was being thrown, but then ignored it, right? So we'd have a try catch, illegal state exception, and then just put ignored, which turned out to be fine because after doing this, I could show that it was never thrown in the first place. So yes, so that became an interesting exercise. So in some cases, there's a few unchecked exceptions for which we will put in temporarily a checked version of the same exception just to see that where it says it's thrown or not thrown is consistent and correct. But then obviously, when you run it, it's an unchecked exception. You don't necessarily need to handle it. And last but not least, a package I've called Onos, which is for handling exceptions. And this one is a somewhat humorous exception handler. And what it does is when you're running on a desktop and you're in debug mode, it will generate a URL which will essentially add the version of Java and the exceptions message, and then do a Google search on the exception that's been thrown to pop up a Google search of the exception that's been thrown. It's kind of fun to play with, but never seen anyone use it in practice.
All right. Well, thank you, Peter, and thanks for everyone who's attended.